Thank you. Yeah, so welcome to the second part. So this part is not really from Lucchesi-Murthy. It is actually some of the work that we did that is related to Birkhoff von Neumann graphs. I want to tell you about a specific one. So let's just remind ourselves that Birkhoff von Neumann graphs are those matching covered graphs for which the perfect matching polytope is equal to the fractional perfect matching polytope, right? And in particular, to decide whether let's consider the decision problem Birkhoff von Neumann. And also let's recall, so maybe decide, given a matching covered graph G, decide whether G is Birkhoff von Neumann, right? This is known to be in co-NP. One graph theoretical way of seeing it as in co-NP is using Balas's result, which says that a matching covered graph G is not Birkhoff von Neumann if and only if there exists an odd conformal bicycle. Yeah? And because of this, or of course you can look at it directly polyhedral if you like, but one way to see it is to this graph theoretical result, which says it means that the problem belongs to co-NP, but it turns out that we don't know whether it belongs to NP and whether it belongs to P. These are open. Yeah. Okay, so that's one problem that we have talked about quite a bit by now, and it suffices to solve the problem for bricks. Let's also make that point, although that point is not too relevant right now, later. Fine. Now I want to tell you quickly about another problem that is actually not discussed in Lucchesi-Murthy, but I am too tempted to talk about it because of this odd conformal bicycle. So, given a polytope, you can define a graph associated with that polytope. For example, why do we call the cube graph the cube graph? Because you take a three-dimensional cube and somehow a three-dimensional cube looks like the cube graph. Let's draw a three-dimensional cube. My drawings are not great, but let me try anyways. No, I don't know, forget it. I'll just draw like this. Okay, this is a cube. That's as good as it gets outside of graph theory. Okay, so given a three-dimensional cube, what you can do is you can take each extreme point, also called faces of dimension 0, and you can make a vertex for each extreme point. So for each extreme point, let's say the extreme points are 0, 1, 2, 3, and 4, 5, 6, 7. Then what I can do is I can put a vertex for each of them. And whenever two extreme points, two corners of the cube if you like, are on a common edge, note that a cube has 8 corners, 12 edges, 12 sharp edges, if I may call them sharp edges, right? Whenever two extreme points belong to a sharp edge, also known as faces of dimension 1, I will put an edge between the corresponding vertices in the graph. So here 0 and 1 belong to a sharp edge, 1 and 2 belong to a sharp edge, 2 and 3 belong to a sharp edge, 3 and 0 belong to a sharp edge, and if you keep doing this, you will get exactly this graph. If I did not make any mistakes in labeling, please check. Yeah. I'm thinking of the 3D cube. Like it will be sharp. If it is made of steel, I might cut my finger. Yeah, I'm just.
It implies the existence of a blunt edge.
Good. Yeah. No, there are no blunt edges, only sharp edges. Yes. Right. But anyways, mathematically speaking, basically what we are doing is we are taking a cube, we are taking its extreme points, which are basically zero dimension faces in the language of polytopes or polyhedra, and we are making vertices for that. And whenever two extreme points belong to a face of dimension 1, we are putting basically an edge between the two vertices, right? This is called the one skeleton of the given polytope. So if this is my cube, this is the one skeleton of the cube. Yeah. So for any polytope, you can construct its one skeleton. That's a graph. Okay. And now you can ask questions about this graph. In particular, I can take the perfect matching polytope of a matching covered graph, and I can ask questions about this polytope. Right? Fine. So that brings me to an interesting property. So we will say that a matching covered graph is PM compact. This is the word some people use, so I will use it. A matching covered graph G is PM compact I will abbreviate to PMC if take the perfect matching polytope, now take its one skeleton, okay, and this is a graph. You took the perfect matching polytope, then for that polytope you took the one skeleton. This is a graph, and is it a complete graph? Let me give you an example where it actually happens. The triangular prism, our so-called standard graph. How many perfect matchings? How many? 4, right? This graph has 4 perfect matchings. This is C6 bar. There are 4 perfect matchings. So when I look at the polytope, it will have 4 extreme points, and you can figure out later. Basically, what you will get is a tetrahedron sitting in R9 because there are 9 edges. Okay, so the polytope, the perfect matching polytope of C6 bar is a tetrahedron in R9, 9 edges.
You're using poly.
Sorry? Oh, sorry, poly. Yeah, thank you. Yes, the perfect matching polytope of the triangular prism is a tetrahedron in R9, and its one skeleton will be, what is the one skeleton of tetrahedron? K4. Its one skeleton will be K4. It's a complete graph. Yeah? Okay, great. You can actually phrase all of this more generally. I will not write down the definitions. I'll just tell you. What you can do is you can take the one skeleton and you can talk about the diameter of the one skeleton. The diameter of a graph, you just take the shortest path between every pair and you take the max overall pairs of vertices of the distance between the two vertices. And this is equal to 1 if and only if the graph is complete. Yeah? So I could have phrased it in a more general way. I could have told you what the combinatorial diameter is, and then I could have asked what is the diameter of the one skeleton. Turns out we don't know in general, but in fact we are going to ask an easier question. Is the diameter equal to 1? In other words, is it a complete graph or is it not a complete graph, right? And even this is not known. So the decision problem I want to pose is now the following decision problem. PM compact, given a matching covered graph, decide whether G is PM compact. And of course at this point it doesn't look very appealing. I mean, you have to take the perfect matching polytope, then you have to take its one skeleton, then you have to check whether that fellow is complete graph or not. I mean, come on, give me a break. It's really annoying. What would be nice is if you can convert this into a purely graph theoretical statement, like we did for Birkhoff or Neumann. No need to think about polytope, you can just think about odd conformal bicycle. Turns out that is true here also. So that's what I want to tell you next without proofs. No proofs in this part. Let's try to think about it. We are checking whether two extreme points. To be a complete graph, it basically means that between the two extreme points, there is a so-called sharp edge. Of course, we are not in 3D anymore. We may be in higher dimensions, right? There is a face of one dimension that contains both the extreme points. The extreme points are just perfect matchings of the original graph. So whether two extreme points are adjacent or not, there should be something equivalent graph theoretically, right? Intuitively you would think that I should just be able to think of something completely graph theoretical and decide whether the two perfect matchings are adjacent in the polytope or not. Yeah? So I have two perfect matchings and I want to figure out whether they are adjacent in the polytope. Adjacent is clear, right? For example, in the cube, these 2 points are adjacent. These are adjacent, but these two, 0 and 2, are not adjacent. Yeah. So we have two perfect matchings, and we want to figure out whether the corresponding extreme points are adjacent in the polytope or not. So if you have two perfect matchings, what do we do in life? Symmetric difference. Whenever you have two perfect matchings in life, consider the symmetric difference. Turns out they are adjacent if and only if the symmetric difference contains exactly one cycle. Clearly the symmetric difference will be a bunch of cycles, right? One or more. If the two perfect matchings are distinct, then you will have one or more cycles. Turns out they will be adjacent in the polytope if and only if the symmetric difference is only one cycle. Okay, so that means if I want the graph to be per PM compact, then the symmetric difference of any two perfect matching should be one cycle, because I want any 2 points to be adjacent, right? I want the skeleton to be complete graph, right? So this is what Chvátal proved. Chvátal and Balinski Russakoff. (1970s) independently. I think Chvátal has an accent. They proved that for a matching covered graph, well, they did not prove matching covered. They probably proved for matchable, but I will state for matching covered. For a matching covered graph, the following are equivalent. 1. The graph is, I wrote not Birkhoff for Neumann. So I'll write not PM compact. The graph is not PM compact is the same as saying that for some two perfect matchings, the symmetric difference contains at least 2 cycles. Okay, and this is a contrapositive of what I said earlier. There exist perfect matchings M1 and M2 such that M1 symmetric difference M2 has at least 2 cycles. Let's look at an example. We can take the cube graph as an example. You can forget the cube, just think about the cube graph. This is a matching covered graph. The symmetric difference has 2 cycles. Therefore, this graph is not PM compact. PM compact would mean for any 2 perfect matchings, the symmetric difference has exactly 1 cycle. Yeah? And now, can you convince yourself, can you actually fill this for me? I want to write something like this, but not exactly the same. Is somebody there? Okay. Okay, but we still have time, right? Yeah, I'll finish it quickly. Right, so it turns out this is exactly even conformal bicycle. It's not too difficult to prove that 2 and 3 are equivalent. 2 and 3 are equivalent is actually quite easy. So, turns out this is the same as saying the graph has an even conformal bicycle. Okay? And this is one way to see that the problem is in co-NP. There are of course polyhedral ways of looking at it, but I am not going to discuss that. Because of this even conformal bicycle, clearly the problem is in co-NP. Once again, the problem is not known to be in NP, and it is also therefore not known to be in P. Yeah? Okay? So now we have 2 very similar open problems. One is about odd conformal bicycles, one is about even conformal bicycles. Yeah? Okay. Now I'll tell you a bit of a story. But I'll keep it short because we are running out of time. So basically, I was in Brazil for what turned out to be one of my most productive visits in life. And on the last day in Campo Grande, which is where Marcelo lives, which is where there are a lot of capybaras, I went for a walk with Marcelo, and he started telling me about some work he was doing with Wang and Lin from China. And he was telling me about some work, and the title of their working paper, this was a working paper not published yet, was Solid Bricks That Are PM Compact. Okay, this was the paper they were working on. They had a complete characterization of solid bricks that are PM compact. For solid, they used the definition, which is of course equivalent to all other definitions. They used that there is no non-trivial separating cut. For PM compact, they were basically using one of these 2, which are very easy to see that they are equivalent, right? I found the problem appealing because I work in matching covered graphs, so I found it appealing. But it was only about bricks. And then I told something to Marcelo that, oh, maybe you can also do this, you can also do that. I told him he can include some more observation in the paper, and he was like, I will invite you to join us. I'm like, no, I don't have anything interesting to say. He's like, no, I'm sure you'll have something interesting to say. I'm like, fine, whatever. I went back to Vienna, he sent me the manuscript, and I started looking through it. And I was like, how will you sell this paper? I mean, publish it, right? You have to sell it to publish it, right? How will you sell this? Who will buy a paper on bricks? I mean, you don't actually have to buy it, but you get the point, right? Who will buy solid bricks that are PM compact? You took 2 classes that are not well understood, then you took that intersection. I mean, why should somebody agree to publish this, right? They might say, no, this is not good enough, not interesting enough. They'll find all sorts of excuses to reject the paper, right? That's how it works. So, my main contribution was to realize that we could solve the whole problem for matching covered graphs, and we could actually find a way to sell it. And for that, I basically, instead of solid, I did solid. I went to Birkhoff for Neumann, which is the same as not having an odd conformal bicycle. PM compact is the same as not having an even conformal bicycle. And now it makes a lot of sense to intersect these 2 classes. One is about odd, one is about even. Well, forget the parity. Can you just ask the question, is there a conformal bicycle or is there not? Can this be answered in polytime? Can you find a characterization of all matching covered graphs that do not have a conformal bicycle? The answer is yes. we have a complete characterization of matching covered graphs that do not have a conformal bicycle, right? And therefore, the decision problem, whether a matching covered graph has a conformal bicycle, that is in co-NP, NP, P, all of them. Because we have a complete characterization, it immediately leads to a polytime algorithm, right? So I can tell you, given a matching covered graph, I can tell you, hey, this has a conformal bicycle, yes or no, I can tell you that. But if there is one, I cannot tell you whether it is odd or even. That is too much to ask for. That is the current state of art. Hopefully in few years we can also talk about the parity, but as of now, we don't know how to talk about the parity. But we can tell you whether there's a conformal bicycle or not. And turns out, you need to reduce the problem to bricks. So that uses the part of the course that we have done so far. You reduce the problem to bricks. That is standard, right? That happens in most problems in matching theory. You reduce it to bricks. Now you actually need to solve it for bricks, which is the part that Marcelo and Wang and Lin had already figured out, right? I did not do that hard part, right? I probably wrote it up again. That's a different matter. But in some sense, the hard part was already done. The bricks part was already done. And for that, there are standard tools, induction tools for bricks. And these induction tools for bricks and braces, Professor Murthy would always tell me, they are nothing but put the tight cut decomposition theory together with the ear decomposition theory, and you take some convex combination of these two theories, and that is the generation theorems of bricks and braces. And at the time, I did not really understand what he meant. I knew both the theories, but I could not see how this was a convex combination of the two. Now I think I see it much more. The second part of this course, which starts on Monday, is going to be dealing eventually with ear decomposition theory. But the way Lucchesi Murthy is structured is they actually go through these things called the dependence relation and removability, and then they talk about the ear decomposition theory in chapter 11. So the next few chapters are going to be dedicated to removability and the dependence relation, right? And maybe at some later point in the course, I will come back to this problem and tell you the solution, right? But if you're interested, there is a video on my YouTube channel, or no, there is a link on my homepage. If you go to my homepage, there's a link called Talks. Under that, there is a bunch of links. One of them is called Birkhoff von Neumann graphs that are PM compact or something like that, or 2 unsolved problems. Just check it out, and that talks about this work. This was a talk I gave in Waterloo. They had a combinatorial optimization seminar, and I was invited in 2020. It was an online talk during COVID. I think it was soon after joining IIT-Madras. So you can check that out if you're interested. Right? And everything should basically be followable given the stuff we have already covered. Yeah. Okay, that's all for today. Any questions or concerns? Okay? Yes, go ahead.
This polytope of cube is also a cube?
The perfect matching polytope of the cube, no. You will have to check how many perfect matchings are there in the cube. Right? So every edge in the cube, every edge in the cube belongs to how many perfect matchings? I have a ladder over here. I take this edge, I have a ladder. Ladder has how many perfect matchings? 1, 2, or I take this, 3. So this edge belongs to 3 perfect matchings. So therefore every edge belongs to 3 perfect matchings. Therefore the cube probably has 9 perfect matchings. And therefore you will get something with 9 points. It will not be the cube, if I did it correctly. Yeah, I think the cube has, because it's basically theta. Theta has 3 perfect matchings. Yeah, the cube has 9 perfect matchings. And therefore the polytope will have 9 extreme points. It will not be the cube. Yeah, good. Okay, any other questions or concerns? Yes, go ahead.
What would be an NP certificate for PM compact intersection? Like
you'll just check that you have to take the retract of the graph, and then you have to check whether it belongs to our family or not.
Oh, that's it.
That's it. Yeah. Okay. Any other questions or concerns? If there are, we can take them offline because we need to erase the board and vacate the room. Thank you. All right. See you all on Monday.